In this video, we'll talk about trapezoidal input into a staff. Alright, later on you'll know what I mean. But if you still remember, we have a trapezoidal staff over here in the integration part, and we say that if you input a certain information with a previous information divided by 2, alright, divided by 2, you have the next input over here, alright, that's coming out over here. So you'll reflect your particular next output. Alright, so after which you input another 2 values, you divide it by 2, you get another stuff over here. Alright, and then you reflect, you have k plus 2 now, this is k plus 1, and then you reflect again using k plus 1 and k plus 2, and go on and go on and go on. Alright, so in this manner we're going to prove to you certain things, alright, such that it'll be clear in terms of the BIBO stability. Right, hopefully this is pretty clear. I don't know. So remember back our l4v7 and v7, I think, right, the videos that we actually touches on the trapezoidal integration and changing it into a transfer function. Alright, this is the path. This is the part where we input, alright, your certain previous output, alright, plus your trapezoidal input in order to get your current output. Alright, put it in a way, and then we rearrange a few stuff. You may not understand what I'm talking just now, alright, but you just take it first, alright, because k minus 1 is a previous output, because u is output, so k minus 1 is a previous output, plus all the inputs that we have back from the current input and the previous input. Alright, that's why everything goes, but I just talking in terms of the k minus 1 and stuff. K minus 1 means that it's the previous, alright, k is the current. So therefore I have a current output over here, UK, right, if you were to look in that perspective. And eventually you get UK as UZ, or maybe it's over here, right, as UZ, with a certain transfer function, and EZ over here. And then you input your own whatever Dirac delta function or whatever over here. So my purpose over here is to show you that this thing eventually becomes this. Alright, so what I can solve is currently to create a Z transform along this whole path over here. Okay, how do I do? So this is the thing over here, and I'll not touch it, and we know that this is the output. Alright, and we know that there is certain inputs, right? E, because E is considered input, U is the output, right? Output, whatever. Anyway, so we can actually deal with the things over here. We can actually Z transform this whole stuff and see how things goes. Alright, this is exactly our HZ times EZ. Alright, we'll get our output. So our EZ, we put in a bounded input, alright, which is a Dirac delta. Alright, this Dirac delta is equals to 1. Alright, if it's k, it should be, alright, maybe this something like this, alright, and then k minus m is equals to z minus m, things like that. Alright, so we have seen this, alright, but we haven't seen what if it interacts with all this and the whole thing Z transform. What will you have? But this is why I want to prove to you that with a bounded input, you may have a chance to get an unbounded output, alright, which is going to infinity. And as for the description, as you can see, I keep I'll keep going up and going up as it's going towards infinity. Alright, it's really can be seen that it's unstable. But I just want to prove to you that how this thing is being so-called, or this perspective is being derived. So let's go. So if I were to Dirac delta, if I were to Z transform this stuff, alright, so this whole chunk over here is simply this thing over here. Okay, so I'm just Z transforming this stuff. You can also Z transform this thing, alright, which is quite fast. Alright, this thing straight away becomes this. That's it. Alright, so we want to look at what is inside over here and see whether is it stable or not. Let's go. So when k is equals to 0, this is the first round. Alright, just write as step 1. The first round, k equals to 0. When k is equals to 0, this is 0 minus 1. Alright, this view is simply just 0. Alright, just take it as that first. Alright, and then t over 2, ek. Alright, e is simply our Dirac delta. Alright, so this is like del k and del k minus m, something like that. Alright, So if you were to do that, if you were to derive delta, you have t over 2, alright, times 1, because it's k equals to 0. Alright, plus, in this manner, you have t over 2 z minus 1 in this case. Alright, which is, wait, sorry, you wouldn't have that, sorry, my fault. Alright, you have just simply that. Alright, multiply with z minus 1. Okay, what am I doing is when I submit as k equals to 0 over here, this thing will become 0 because there's no information from the previous, because we are just starting up only. Alright, and then you apply a direct delta, which is when k equals to 0. Direct delta means that when k equals to 0 is 1, so 1 times t over 2, t over 2. Alright, and this is k minus m. Alright, so in this case it's k minus 1. So if my k is equals to 0 in this case, then actually this thing will not work. This thing is still 0, because if k equals to 1, if so becomes delta 0, then this will become 1. Alright, and therefore this shall exist. Alright, but since this is not 1, this is just 0, this whole thing becomes 0. So therefore it's just simply t over 2 times 1, that's all. Okay, and the z minus 1 is just simply over here. Okay, so this is the first series. As you can see, this series is super long already. Alright, and later on, that's why it's pretty tough to prove, but just to show you. This should be minus k, because if you were to do in terms of a z transform, this is minus k. I don't know why I keep putting minus 1. Alright, if this is minus k, if it's k equals to 0, then 0 is actually 0. I mean 1, sorry. So therefore this is actually 1. Alright, times 1 over here. Alright, so this is our first series. And if you happen that you don't know what I mean, if let's say for example, if you still remember this equation, this is the series that we are doing, because this is the z transform. You are z transforming ek, right? For example, this although this ek is not our delta, alright, I'm just taking the general formula for the z transform. So this, if you z transform ek using these parameters, you have e0 plus this thing, right? If you still remember. And what we are doing now is actually the first round, which is this one, is actually this one. Alright? So we talk so much, we're just only talking about the first number, when k is equals to 0. Now we're going to talk about this one, and later on we can generalize the rest and see how it goes. Alright? So let's just keep this and get a feel of it. So I'll just change a different color for better understanding. Alright, just draw a line, at least it's more dissect. So when ak equals to 1, right, you 1 minus 1. So this is the previous, so it's talking about u0, talking about our current output when u is 0, right? Because when k equals to 0, this is u0, alright, so it's u0 over here. So therefore, when k equals to 1 now, u0 is our simply t2, ta-da, t2 over here, and then plus, alright, now I should, okay, t2 times e1, alright, e1. So since this is e1, this one will become 0 because the right delta function doesn't exist over here. Alright, because the right delta only exists when k is equals to 0. When delta, this whole thing is 0, then it is 1. So in this case, is if this is 1, or in other words, if you still remember the graph, this is the point, if you still remember. So the rest are all 0 except this point 1. Alright, so when k equals to 0, then you have a spike. Alright, so therefore when k equals to 0, when k equals to 1, then this whole thing is becomes 0 because there is no signal already. It's a direct delta input. Alright, and then now we have k equals to 1 now. So right, so this is k minus 1 in this case, right? Because our equation tells us that we have a k minus 1 over here, so this is direct delta k minus 1. Alright, so if it's 1 in this case, then 1 minus 1 is 0. So therefore, the direct delta function zoom up again. Bam. Okay, so when you zoom out again, what you will have is t over 2 times 1. Right, so it's just t over 2 times 1. And then we have, instead of z minus k is equals to 0, we have z minus k is equals to 1. Therefore, it's z minus 1. So this will be your next input, u1. Okay? Next, if I were to sub in as k is equals to 2 now, right, when k equals to 2, so u2 minus 1 is u1, right, u1 is simply your previous input, alright, so it's just your t over 2 plus t over 2 is your t, right, is t z minus 1, okay, plus, alright, when this is, alright, this is disfigured, but this is 2 in this case, the delta function actually off, it becomes 0, alright, and therefore this becomes 0, and this is also 2 minus 1 is 1, alright, this is also not 0. When you see the, although like k minus m or k like this, if it's equals to m, this one will becomes 0. If k is equals to 0, this is 0 also. So whenever you see this thing exists, you just have a 1 over here, and then you multiply with whatever that is constant. So in this case, we don't see any 1 anymore, right? Because this is 2 minus 1, we have equals to 1. So therefore, this is not 0, and therefore the Dirac delta is not activated. Alright, same as this is ek, alright, I mean delta k, if we were to say. So delta k only activate is being when it is equals to 0. If it's equals to 2, 3, 4, it's all 0. So therefore, this whole chunk over here is still 0. Alright, later on subsequently you will know that these things will never on again. Alright, this thing will never on again. The only thing that runs is only this thing. And therefore later on you get what I mean already. Alright, so this thing now we know that this whole thing is 0. 0 times c over 2 is still 0. Alright, and let's write 0 over here. Multiply by, since this is k equals to 2, so this is z minus 2 now. So I have z minus 2, which is equals to u2. Alright, next I sub in my u2 as my next, sorry, what am I talking? Next color. If you don't know what I mean, you just hang on, later on you'll get a full picture. Alright, when k is equals to 3, same thing, when this is 3 minus 1 is 2, so it's u2 now. So you just sub in as u2. Your u2 is simply your tz minus 1 times z minus 2. So you just simply tz minus 3, okay, plus, alright, as we say earlier, this one will never exist anymore, because the Dirac delta function will never become Dirac 0 anymore. Alright, it's always delta 1, delta 2, 3, 4, 5 anymore, all the way already. So we know that only delta 0, when delta 0 or k equals to 0 exists, you'll have this thing on, the rest off. Hopefully this one you understand. If otherwise, you should go back and watch the Dirac delta. This might ring some bell to you. But anyway, this whole thing will still becomes to 0. Right? This whole thing will still becomes to 0. And therefore it's still 0. And if it's k equals to 3, z minus 3 now, alright? So therefore I'll just simply write as z minus 3. Alright, is equals to u3. And so on. As you can see, the trend start to appear already, right? It keeps on looping the t now, right? So for the 5, it's just k equals to 4, and then your loop is just t minus 4 plus 0. You see z minus 4 now is equals to u4. Alright, as you can see, that the trend is starting to appear for you. Alright, so let's just finally we can see something, right? So as you can see, the first sequence when k is equals to 0, alright, is actually this one. Alright, it's t over 2, so I just put it as t over 2. Plus, the next sequence over here is your next stuff over here, where it's k equals to 1, right? It's k equals to 1. So, when k equals to 1, this is my stuff. So t over 2 plus t over 2 is actually t, right? So it's just t z minus 1. Right? Plus, alright, this is the when k equals to 2, because as you can see, this is 2 over here. So when k equals to 2, we have tz minus 1, right, times z minus 2. Alright, what you have is tz minus 3. Okay? And then now if it's k equals to 3, alright, which is e3 now, alright, then you have tz minus 3 times z minus 3, right? So we have tz minus 6, and so on and so forth. And this z minus 6, z minus 3, and z minus 1 is simply telling you that they are actually one time step delay. Alright, it's totally not related to your magnitude. Your magnitude is always t. Alright, your magnitude now is always t. And this also explains why in the lecture it keeps saying that the first thing is t over 2, then t. This is the reason behind the t is this t's. Alright, and therefore these are all thumb steps. So if I were to just ignore the thumb steps but just taking out their magnitude, t over 2, t, and t, if I sum it up all together, they go into infinity, because summation over here, if you still remember, we are summing up all the stuff. And therefore when you summation, you will get equals to infinity. And therefore we prove that the trapezoidal stuff is actually a unbounded output. Alright, and therefore BIBO not stable. Okay, so therefore you may wonder, what the hell am I doing so long? But the key concept that I just want to convey is this. If you still remember all the way back for the integration, dealing with the Fibonacci series. Alright, the Fibonacci series states that the first two numbers, if you add up together, you have 1. Alright, 0 plus 1 is 1. And then subsequently, these two numbers, if you add up, you have 2, and then 3, 5. So this 2 plus 1, you have 3. Then 3 plus 2, you have 5. 3 plus 5, you get 8, and go on. It goes to infinity if you plot it out. Alright, so what we're doing now is actually the same thing. This is the previous output, which is 0. Alright, this is the next input. Anyways, similar things. Alright, so 1, and then now the next round, 1, you input a new 1, and then 1 plus the previous stuff 1, so it becomes 2. So 2 now is you input over here, and then 2 plus the previous stuff is 1, so you have 3. So 3 becomes your previous, should be previous input 3, and then plus your previous output 2, so you have 5. Maybe I should repeat again, you may like killing me right now, right? So this one is my initial input 0. This is my output 1. Alright, so in the end I have 1 over here. Alright, this one I'll input for over here as 1. Okay, and then I input this value as 1 over here. So 1 plus 1 is 2. Alright, so this 2 I'll fig back over here as 2 now, and then 2 plus a new where am I? Input 3. What I have is 3 plus 2, it's 5. You can just check it out lah. It's just a Fibonacci number. You just think about it. This is the best way I can explain to my I'm damn tired already. Anyway, so what we have, this thing over here, alright, is in terms of your output previously plus your input plus all your inputs lah, alright, your previous input and your current input. Alright, so therefore with seeing this type of equation dealing with output and input, the first thing first is UK is straight away your UZ, alright, your transfer function in terms of transfer function. And HZEZ, right, is simply this one over here. Alright, so if you want to so-called find the stability, the bounded output, whether is it a bounded output system, then you're gonna use what we have done. We just try to do all this stuff. You apply your Z transform formula, and then you go on with all this series, and then you just simply sub in your k equals to 0 and 1, things like that. Or you can click back a few minutes or 10 minutes ago, and then you just rewatch back until you may have a sense of it. Alright, and this is just applying your formulas and Z transforming the whole stuff over here. Alright, instead of if you might be bounded by your own understanding for this one, it's because we actually created a Z transform one by one. We actually Z transform one by one, and then we all the way come here. Alright, you can do that, but I don't think we can derive that particular same answer as that. Alright, this is the way to derive a transfer function, but might not be exactly the way to actually derive whether a system is bounded input or bounded output. And therefore you need to conduct a really huge tedious way to actually prove that it is bounded. Whether is it a BIBO stable or unstable. Alright, and yeah, this is it, and I hope that this is pretty helpful, and I shall see you soon.